Oh, there's something in my chest that I can't hide. When feelings get involved, I'm terrified. 'Cause I've been here before and said goodbye. Oh, are you the one when I try to look, I wish I'd find? Oh, how can I love when I've been hurt 100 times? But you would give it one more try. Turn away and wrestle with my doubts. Oh, I leave them all behind, but don't know how. Bury my head deep within the crowd, but I'm reaching for your hand to pull me out. Oh, are you the one when I try to look, I wish I'd find? Oh, how can I love when I've been hurt 100 times?
Alrighty, folks. Hello. Where are my captionings? Oh, of course. My caption link ran out. It would not be a normal stream without my damn captions running out. And I really am going to have to find a new captioning software, because this one is sunsetting October 31st this year. So, that'll be something I need to work on. All right. So, we get to start in on the Time Travel Handbook, a manual of practical teleportation and time travel. Edited by David Hatcher Childress, the Lost Science series. So, I don't know what you think of David Hatcher Childress. You may not know who he is. You may know who he is and think he's either fantastic, a great researcher. You might think he's a complete whack job. You might think he just makes everything up. And you may be right in any one or all of those opinions. I get a kick out of his stuff, whether it's true, whether he makes some leaps, doesn't really matter. It's still enjoyable reading. So, yeah, let's get into his book. So, the very first, well, it starts out on page 9, actually, and on page 8, the facing page is just another version of that cover art, just in black and white. Okay. All right. Chapter 1, The Fundamentals of Time Travel, from Quantum Mechanics to Superstring Theories. It starts off with 2 quotes. The first one, time travels in diverse paces with diverse persons. I'll tell you who time ambles withal, who time trots withal, who time gallops withal, and who stands still withal. William Shakespeare. The next quote, the consciousness of man has an extended nature which enables him to surpass the ordinary bounds of space and time, suggesting that there is another dimension beyond the material world, and that is Edgar Mitchell, former astronaut. Historical theories on time and gravity. Welcome to Time Travel 101. Throughout history, there have been many attempts to describe or explain gravitation, as well as the phenomena of time, sometimes referred to ancient philosophical texts as, quote, the arrow of time, end quote. In order to gain a full understanding of time travel, it is important to grasp historical theories of time, gravity, and what is now termed the unified field. The various physical forces surrounding us are little... That's why things feel out of whack. Okay. The various physical forces surrounding us are still little understood. Each year brings us closer to understanding the amazing universe around us and how it works. The interaction with space-time and the so-called quantum field that is everywhere. Finding hyperspace wormholes and other time tunneling devices are the natural product of understanding how the universe works. And a strange universe it is. Although Western society has gone through a number of dark ages, as far back as 330 BC, Aristotle claimed that the 4 elements, earth, water, air, and fire, have their natural places toward which they tend to travel. He argued that objects containing greater amounts of earth than others would fall toward the earth faster, and that their speed would increase as they neared their natural place. Galileo Galilei deduced in 1604 that gravity imparts a definite acceleration rather than a velocity, and that this acceleration is the same for all objects traveling in a vacuum. The universality of gravitational acceleration is known as the weak equivalence principle. Sir Isaac Newton made the most significant contribution to gravitational theory when he perceived in 1606 that the orbit of the moon depended on the same type of force that causes an apple to fall to Earth. This proposition required that the magnitude of the force decrease in inverse proportion to the square of the distance from the Earth's center. Newton combined the inverse square law with his 3 laws of motion to formulate a theory of universal gravitation, which stated that there is a gravitational attraction between every pair of objects inversely proportional to the square of the distance between them. Did you get all that? René Descartes, 1596 to 1650, had earlier proposed a non-quantitative theory of gravitation, based on the inward pressure of vortices on planets, but Newton did not offer a cause for the attraction. In effect, he avoided even calling it an attraction, speaking instead of, quote, bodies gravitating towards one another, end quote. This description was sufficient to deduce Kepler's laws of planetary motion, the oceanic tides, and the precession of the equinoxes. In 1846, it was used to predict and discover a new planet, Neptune. Thus, Newton's theory of gravitation stands as one of the greatest advancements of scientific knowledge. Expressed mathematically, Newton's theory states that there is an attractive force, F, given by F equals gm 1 m2 slash, or divided by, r, I guess that's squared, r2. Not a not a mathematician by any means, between two particles having masses m1 and m2 and separation distance r. G is the gravitational constant of proportionality, an unknown quantity that could not be determined by solar system observations, which gave only ratios of masses, and thus the product of G and some mass. The value of G was first determined in 1798 by Henry Cavendish, who measured the force of gravitational attraction between two spheres of known mass. This experiment has come to be known as weighing the Earth, because once G was determined, the Earth's mass, m e1, could be determined from the astronomically known value for gm e. Parentheses e. The experiment has been repeated many times with increasing precision. The currently accepted value of G is 6.67259 times 10 to the negative 8 cm parentheses 3 divided by G little g. So is that centimeters cubed by G seconds, SEC, with a 2 in parentheses. Again, not a mathematician. Don't understand quite all of that notation. Modern theories. In 1905, Albert Einstein developed his theory of special relativity, which modified Newton's theory of gravitation. Einstein sought to describe gravitation in a way that was independent of the motion of observers and of the coordinates chosen to label events. His work led to a geometrical theory that described gravity purely by the structure of the space-time continuum. According to this geometrical theory, gravity affects all forms of matter and energy, all of which move in space-time. Thus, Einstein's theory obeys the weak equivalence principle and gives the same gravitational acceleration for all freely falling objects. In addition to describing the effects of gravity on matter, Einstein described the effect of matter on gravity. This theory, which Einstein completed in 1915, is called general relativity. Although Einstein's theory is much different from Newton's, it predicts nearly the same effects in systems in which gravitational fields are weak and velocities are slow compared to the velocity of light. Planetary motion had provided a particularly accurate verification of Newton's theory, but Einstein's accounted for some phenomena in the solar system not considered by Newton. One such phenomena was the perihelion precession of Mercury. In the 19th century, it was observed that the rate of precession differed by 43 inches per century from what Newton's theory predicted. Einstein's theory predicted precisely such a difference in the precession rate. Another such phenomena is the bending of light rays by the sun's gravitational field, which Newton's theory did not predict at all. Einstein's prediction was confirmed by Arthur S. Eddington during a total eclipse in 1919, and later by others to 1% accuracy. Einstein also predicted the gravitational redshift, a change in the frequency of electromagnetic waves escaping from a strong gravitational field, which was confirmed by Robert Pound and Glenn Rebka in 1960. In 1964, Irving Shapiro used general relativity to predict a time delay of signals passing near the sun, an effect since confirmed. In addition, Einstein's theory of general relativity predicts several qualitatively new effects in other systems, and is especially useful in dealing with cosmology. Relativity asserts that the universe must be either expanding or contracting. Einstein was not sufficiently bold to believe this prediction, however, so he modified his equations to allow for a static universe. In 1929, though, Edwin Hubble discovered that the universe is expanding. Whether gravity will eventually cause it to collapse is a subject of current investigation and debate. General relativity also predicts gravitational waves from masses in non-uniform motion, but these waves are so weak that they have not yet been definitely detected. Finally, Einstein's theory predicts gravitational collapse of sufficiently massive objects into black holes. Today, there is a mounting evidence that several astronomical systems may contain black holes. Actually, just out of curiosity, I want to see what year he was writing this in, if it says. Because a lot... Oh, in 1999. So they've found out a lot more about black holes since then. All right. Einstein's general relativity is not the only 20th century theory of gravity, though it is perhaps the simplest and most elegant. All viable theories of gravity must, like Einstein's, be complete, self-consistent, and relativistic. They must also have the correct Newtonian limit, uphold the weak equivalence principle, and predict the same Einstein shift as measured by all ideal clocks at the same position. There is strong experimental evidence for accepting these criteria as fundamental, and it has been conjectured by L.I. Schiff that they can be satisfied only by geometrical or metric theories. The strongest rival theory has been the Drans-Dickey theory. Like general relativity, it is a geometrical theory that satisfies the fundamental criteria. Its field equations are different, however, and it claims that the geometry of space-time is affected not only by matter but also by an additional scalar field. Unlike Einstein's calculation, the Brans-Dickey theory cannot predict the perihelion shift of Mercury. Some recent theories attempt to explain gravitation non-geometrically, proposing instead that particles called gravitons are responsible. These are called supersymmetry theories. These so-called supersymmetry theories place gravitational phenomena within the realm of quantum physics. They are part of an attempt to show that the four fundamental interactions of nature are related, and that they were a single united force at the birth of the universe. Multidimensional analysis has also raised the issue of the constancy of the gravitational constant, g. This idea was proposed earlier by British physicist Paul Dirac in his so-called large numbers hypothesis. Dirac noted that the ratio of the strength of the electromagnetic force is that of the gravitational force, approximately 10 parentheses 40, so I guess 10 to the 40th is what he means, is roughly equivalent to the age of the universe in atomic terms. He wondered whether there might be a deep physical connection requiring this similarity, and proposed that this would be the case of if G slowly decreased as the age of the universe increased. If G were decreasing, however, gravitational time would change with respect to atomic time. Thus far, experiments have not shown this to be happening. Unified field theory. In theoretical physics, a unified theory may be defined most broadly as a theory that, with one set of equations, would unify all four of the fundamental interactions of nature: gravitation, electromagnetism, and strong and weak nuclear forces. No such all-encompassing theory yet exists. Historically, the term unified field theory was first given to the attempts of Albert Einstein to unify two of the fundamental forces, gravitation and electromagnetism. That is, after presenting his theory of gravitation, the general theory of relativity, he set out to reconcile his results with the description of electromagnetism given by the famous set of equations of James Clerk Maxwell. Einstein's idea was to combine his and Maxwell's descriptions by treating both subjects from an essentially geometric point of view. He failed to achieve this goal. This failure, however, must be judged in light of the fact that at that time the strong and weak nuclear forces had not yet been discovered. Other attempts to incorporate electromagnetism into the basically geometric formalism of general relativity were made by the German physicist Hermann Weyl. Weyl. And the American John Wheeler. Although some of their theories are more aesthetically pleasing than others, all lack the connection with quantum phenomena. That is so important for interactions other than gravitation. Later attempts at unification have been made from the quite different point of view of merging the quantum field theories that describe, or are supposed to describe, the four fundamental interactions. The most successful thus far has been the electro-weak theory of Sheldon Glashow, Steven Weinberg, and Abdus Salem, which joins electromagnetism and the weak interaction. In the simplest version of this theory, forces are transmitted by the exchange of four different types of particles called bosons, which are assumed to be massless. By means of a, quote, broken symmetry, end quote, an effective generation of mass occurs with three bosons, W plus, W minus, and Z0, I guess that means neutral, particles, having masses on the order of 50 to 100 times the mass of the proton, and a fourth boson, the photon, remaining massless. The W and Z bosons were detected by high-energy experiments at the CERN laboratories in 1983. Weinberg, Salem, and Glashow shared the 1979 Nobel Prize for Physics for their model. Many other unified theories have been proposed beyond the electro-weak theory. Some try to involve the strong interaction, and some quote-unquote theories of everything try to include gravitation as well. The later are also known as supersymmetry theories. None have been successful as yet. Quantum mechanics. According to Einstein's general theory of relativity, nothing can travel at the speed of light or greater speeds. However, quantum mechanical theory allows for a phenomenon called tunneling that, in theory, would provide a method of moving one place to another at speeds greater than light. William Corliss mentions that in 1995, German researchers claimed to have transmitted Mozart's 40th Symphony a short 5 inches, but at 4.7 times the speed of light. Quantum mechanics is the fundamental theory used by 20th century physicists to describe atomic and subatomic phenomena. It has been successful in tying together a wide range of observations into a coherent picture of the universe. While quantum mechanics uses some of the concepts of Newtonian mechanics, the previous description of physical phenomena, it differs fundamentally from the Newtonian. For example, in Newtonian physics, quantities are believed to be continuously variable, able to take on any value in some range. An example is angular momentum, which, for a particle revolving in a circular orbit about some center of attraction, is proportional to the speed multiplied by the distance from the center. Because that distance could have any value in Newtonian mechanics, so could the angular momentum. In quantum mechanics, on the other hand, angular momentum is always restricted to certain discrete values whose ratios are simple rational numbers. An even more fundamental difference between quantum mechanics and previous physical theories is that probability enters in a basic way into how quantum mechanics describes the world. This is made evident by the way that quantum mechanics and Newtonian mechanics deal with predictions of the future. For example, for something described by Newtonian mechanics, such as the solar system, it is possible, if sufficiently accurate measurements are made at one time, to predict the future behavior of the system to arbitrarily great accuracy. For systems described by quantum mechanics, even one as simple as an atom with a single electron, precise prediction of future behavior is usually impossible. Instead, only predictions of the probability of various behaviors can be made. This can be illustrated by the description of an unstable radioactive nucleus. Quantum mechanics does not predict when the individual nucleus will decay, although in many similar nuclei, if many similar nuclei are surveyed, one can predict what fraction will decay in any time interval. This novel feature of quantum mechanics, known as indeterminism, has been one of the things that has led some prominent physicists such as Albert Einstein to resist it. Nevertheless, it appears to be an unavoidable feature of physics at the atomic and subatomic levels. Yes. Hey, Nambro, how's it going? Okay. Early historical development, Planck's work. Quantum mechanics was developed over a period of 30 years, during which it was successfully applied to several physical phenomena. The first use of quantum ideas was made in the analysis of how electromagnetic radiation is produced. This was done by the German physicist Max Planck in 1900. Planck was trying to account for the distribution among different frequencies of the radiation emitted by a hot object, such as the surface of the sun. He found that to obtain results in agreement with observation, he had to assume that the radiation was not emitted continuously, as was previously believed. Instead, it was emitted in discrete amounts, which he called quanta. For these quanta, there was always a relation between the frequency f and the amount of energy emitted, E, of the form E equals hf. Here, h is a universal constant introduced by Planck and now named after him. Planck's constant has the units of energy multiplied by time, known as action. In numerical value, it's approximately 6.63 times 10 to the negative 34th joule seconds. The specific result of Planck's analysis was a formula expressing the amount of energy radiated at any frequency as a function of the temperature of the emitting object. This relation, the black body distribution, agrees accurately with observation. In Planck's theory, the nature of the quanta was rather mysterious. It was clarified by the work of Einstein, who in 1905 proposed that light itself was composed of individual packages of energy, which later came to be known as photons. Einstein also proposed that the frequency of the light is related to the energy of the photons composing it by Planck's formula. Einstein's theory of light quanta, which was rejected by many of his contemporaries, including Planck, was verified both by Robert Millikan's work on the photoelectric effect and by the discovery by Arthur Compton of the Compton effect, or the scattering of photons by electrons. Another significant early use of quantum ideas was by Niels Bohr, or Niels Bohr, no, I think it's Niels, who in 1913 showed that by assuming that the angular momentum of electrons in a hydrogen atom could only take on values that are an integer multiple of Planck's constant divided by 2 pi, he could derive accurate expressions for the frequencies of light emitted by the atom. Bohr's analysis implied that only certain energy values are possible for the electron in the atom, that there is a minimum value, and that in this minimum energy state, the electron cannot radiate energy. This result helped explain how the atom could be stable and how all atoms of one element have the same chemical properties. However, it proved impossible to extend Bohr's ideas directly to atoms more complex than hydrogen. Also, the strange blend of Newtonian and quantum ideas left physicists uneasy about the supposedly basic principles of their science. Forms of quantum mechanics. The development of actual quantum mechanics, the mathematical theory, took place in the years 1924 through 27. Initially, there were two seemingly different approaches: matrix mechanics, invented by Werner Heisenberg, and wave mechanics, invented by Erwin Schrödinger. However, it was soon known that these were distinct aspects of a single theory, which came to be known as quantum mechanics. This unified version was invented by Paul Dirac. In matrix mechanics, physical quantities such as the position of a particle are represented not by numbers but by mathematical quantities known as matrices. Matrix mechanics is also useful in dealing with situations in which there is a small number of relevant energy levels, such as a particle with definite angular momentum in a magnetic field. Wave mechanics is more useful in a situation where the number of energy levels is infinite, as with an electron in an atom. It is based on the idea originally suggested by Louis de Broglie that particles such as electrons have waves associated with them. The wavelength gamma of the wavelength gamma of the wave is related to the mass m and speed v of the particle by the relation gamma equals h divided by mv. This implies that for electrons moving at 10% the speed of light, such as those produced by some television tubes, the wavelengths are about 10 to the negative 10 meters, or about the distance between atoms in a crystalline solid. This prediction of de Broglie was verified by Clinton Davison and by George Thomson, who were able to pass the electron waves through metallic crystals and to produce diffraction patterns similar to those produced by X-rays. In 1925, Erwin Schrödinger developed an equation now bearing his name, which describes how a wave associated with an electron or other subatomic particle varies in space and time as the particle moves under the influence of various forces. This equation has many types of solutions, and Schrödinger imposed the condition that for a particle bound in an atom, the solution should be mathematically well defined everywhere. When applied to the case of an electron in a hydrogen atom, Schrödinger's equation immediately gave the correct energy levels previously calculated by Bohr. However, the equation could also be applied to more complicated atoms and even to particles not bound in atoms at all. It was soon found that in every case, Schrödinger's equation gave a correct description of a particle's behavior, provided that the particle was not moving at a speed near that of light. In spite of this success, the meaning of the waves remained unclear. Schrödinger believed that the intensity of the wave at a point in space represented the quote-unquote amount of the electron that was present at that point. That is, the electron was spread out, not concentrated at a point. However, it was soon found that this interpretation was untenable, because even if a particle was originally concentrated on a small region, in most cases, it would soon spread over an increasingly larger region, in contradiction to what was the observed behavior of particles. The correct interpretation of the waves was discovered by Max Born while studying how quantum mechanics describes collisions between particles. He realized that the intensity of the de Broglie-Schrödinger wave was a measure of the probability of finding the article at each point in space. In other words, a measurement would always find a whole particle rather than a fraction of one, but in regions where the wave intensity was low, the particle would rarely be found, whereas in regions of high intensity, the particle would often be found. Heisenberg's uncertainty relation. An important contribution to the interpretation of quantum mechanics was given in 1927 by Heisenberg. He analyzed various, quote, thought experiments, end quote, that were designed to suggest information about the location and velocity of a particle. An example would be the use of a microscope to image an electron. It is known that because of the wave properties of light, a precise electron image requires the use of light of very short wavelength, and therefore high frequency. However, the Planck-Einstein relation implies that for such light, the photons must carry a large amount of energy and momentum. In the collisions between such photons and electrons, the electron momentum will be changed uncontrollably from what it was before the collision. As a result, the increased precision with which the electron's position is known is unavoidably accompanied by a loss of accuracy in the knowledge of its momentum. On the basis of this and related analyses, Heisenberg was led to formulate his uncertainty principle, which in its simplest form states a reciprocal relation between the uncertainty delta x with which we can know the position of any object, and simultaneously the uncertainty delta p with which we can know its momentum. The mathematical statement of the uncertainty relation is given by delta x delta p is less than h divided by 4 pi. For an object of everyday size, this limitation on simultaneous measurements is very unimportant when compared to ordinary experimental uncertainties. For this reason, there is rarely any significant difference between the predictions of Newtonian and quantum mechanics for such objects. However, for an electron in an atom, the uncertainty restrictions are so significant that they essentially determine both the size and the minimum energy of the atom. I didn't realize this was going to be quite so physics heavy in this first chapter. But, you know, that's fine. It just... a lot of physics and math. Where was I? Where the hell was I? I completely lost my place. I'm sorry. Oh, the energy of the atom. Okay. Blech. Sorry. I didn't stop at a normal stopping point. Okay. With Born's probability interpretation of the wave intensity and Heisenberg's uncertainty principle, the elements of the standard indeterministic interpretation of quantum mechanics were in place by 1930. This interpretation is often known as the Copenhagen interpretation because Niels Bohr, who made important contributions to its formulation, ran an influential physics institute there during this period. However, many physicists, including Einstein and Schrödinger, who accepted the mathematical formulation of quantum mechanics, were uncomfortable with the Copenhagen interpretation and criticized it. The question of the correct interpretation of the mathematical formalism has remained something of a problem. Directly after its discovery, quantum mechanics was applied to many problems in atomic physics and chemistry, such as the structure of many electron atoms and of molecules. These applications were generally successful in explaining old observations and in predicting newer ones. An example of the later case was the successful prediction that hydrogen molecules could exist in two types. depending on the relative orientation of the angular momentum of the nucleus. This type of success led Paul Dirac in 1928 to describe quantum mechanics as, quote, including all of chemistry and most of physics, end quote. Although the second half of this statement has not proved to be perfectly accurate, extensions of quantum mechanics have been successful in explaining an ever-growing number of physical phenomena. For example, in the 1930s and 40s, George Gamow used quantum mechanics to explain radioactive alpha decay of atomic nuclei. In some applications to atomic nuclei and for accurate calculations in atomic physics, it became necessary to extend the original form of quantum mechanics to make it consistent with Einstein's special theory of relativity. This was first done by Dirac in 1927 with an equation bearing his name. Dirac's equation proved immediately successful in accounting for a property of electrons known as spin. Spin in angular momentum of rotation about an axis through the electron, somewhat like that of the Earth rotating about its own axis. It was obviously known that all electrons carry a spin of h divided by 4 pi, but the reason was not clear. The Dirac equation explained this and accurately accounted for some magnetic properties of spinning electrons. It also made a novel prediction of the existence of particles similar in mass and spin to electrons, but with opposite electric charge. These particles, which have come to be known as positrons, were discovered by Carl Anderson in 1932. They were the first example of antiparticles whose existence is predicted by any theory that satisfies the requirements both of quantum mechanics and special relativity. Quantum field theory. The study of antiparticles and their properties highlighted a new aspect of relativistic quantum theories: the creation and annihilation of matter. Dirac had predicted and it was soon observed that electrons and positrons could be created together in pairs when high-energy photons pass through matter. Furthermore, a positron that comes near to an electron quickly disappears together with the electron, converting into several photons. In order to describe transformations in which the number of particles changes, it was necessary to apply quantum mechanics to a new area, that of fields. In Newtonian physics, a field represents a physical quantity, such as electric force, which varies from point to point in space and time according to precise mathematical equations. Such classical fields can have any numerical value at any point. The general version of quantum theory was first applied to the electromagnetic field by Dirac, who showed that this combination automatically implied the existence of photons with the properties assumed by Planck and Einstein. Furthermore, Dirac was able to use this quantum field theory formalism, which came to be known as QED, or quantum electrodynamics, to describe how photons are emitted and absorbed by charged particles, as when an electron in an atom radiates. An important practical application of QED in the late 1950s was the invention of the laser. A number of physicists applied similar ideas to other previously unknown fields in order to describe processes in which the number of other types of particles change. For example, Enrico Fermi in 1933 used quantum field theory to explain the emissions of electrons from a nucleus, the process known as beta decay. The general lesson learned from this is that fields satisfying the laws of quantum mechanics and relativity automatically describe particles that can be created or destroyed. quantum field theory had some unforeseen consequences. One aspect of Heisenberg's uncertainty principle is that the law of conservation of energy is not strictly observed for short periods of time. Because of this, a particle such as an electron can briefly emit and then reabsorb other particles such as photons. These transients, called virtual particles, influence the properties that we measure for the electron. In particular, they change its mass from what it would have been if they did not exist. The extra mass due to virtual particles is called the self-mass. Unfortunately, when physicists in the 1930s tried to calculate the self-mass due to virtual photons, they got an infinite result. For some time, this result paralyzed progress in quantum field theory. However, in the 1940s, a method was found for dealing with infinite self-mass and certain related infinities. This procedure, known as renormalization, has dominated quantum field theory since that time. Renormalization. The idea behind renormalization is that the self-mass is not directly measurable. Only the combination of self-mass and any intrinsic mass that the electron might have can be observed. It was suggested excuse me. Excuse me. It was suggested first by Hendrik Kramers that an infinite self-mass might combine with an infinite intrinsic mass to give the infinite observed mass. It should then be possible to express all other observable quantities in terms of this sum, avoiding the problem of infinities. Calculations involving this procedure, known as mass renormalization, are quite delicate to carry out. Indeed, they were only done successfully after new techniques were introduced in the late 1940s by Julian Schwinger and Richard Feynman. These methods are designed to be consistent with relativity theory at all stages, unlike earlier methods, which made sharp distinctions between space and time. Feynman's method involves the use of suggestive pictures now called Feynman diagrams, which are correlated with any process to be calculated. For example, the emission of a photon by an electron is pictured as a solid line of indefinite length, representing the electron, which with a wavy line, representing the photon originating in the middle of the electron line. Feynman described a set of rules by which the probability of occurrence of any process could be calculated directly from the associated diagram. In the late 1940s, using the methods of Feynman and Schwinger, scientists calculated small corrections due to emission and absorption of virtual photons, for the energies of electrons in hydrogen atoms, and for the magnetic properties of electrons. These calculations, which have continued to ever higher levels of accuracy, in some cases agree with observation to the incredible accuracy of 1 part in a billion. This is probably the greatest triumph that theoretical physics has yet achieved. Again, this is in 1999. The success of QED led many physicists to believe that other renormalization quantum field theories could be found to describe properties of subatomic particles that are not included in QED, such as the strong forces that bind neutrons and protons into nuclei, and the weak forces responsible for beta decay. For many years, this hope was not realized because not enough was known either about types of renormalizable theories or about the particles to which such theories should be applied. This situation changed in the 1960s and 1970s following the invention of Chen-Ning Yang and Robert Mills of a particular kind of renormalizable quantum field theory known as a gauge field theory. It was shown that one type of gauge field theory named quantum chromodynamics, or QCD, was capable of describing the strong interactions, provided that it was applied not to protons and neutrons, but to quarks, hypothetical particles that compose protons and neutrons, and other particles affected by strong interactions. A second gauge field theory was shown by Sheldon Glashow, Stephen Weisberg, and Abdus Salem to be capable of describing electromagnetic and weak interactions together, thus unifying in a single theory two important aspects of nature. In spite of the success of renormalizable quantum field theories, some prominent theoretical physicists such as Dirac have expressed misgivings about them. Although observable quantities are finite in these theories, this is achieved through manipulations with infinite quantities that are mathematically suspect and aesthetically unpleasant. The interpretation of quantum mechanics, hidden variable theories. Quantum mechanics is now over 60 years old and has been very successful in providing explanations for physical phenomena. Nevertheless, there remains a dissatisfaction among some physicists both with the theory itself and with the prevailing Copenhagen interpretation. Much of this criticism derives from the radical change from earlier theories that quantum mechanics represents. Some of it involves problems that arise within quantum mechanics itself. One criticism of quantum mechanics relates to its indeterminacy. This was Einstein's original objection, although he later developed others. Because an individual radioactive nucleus will eventually decay at a specific time, Einstein and others believed that a complete physical theory should allow this time to be predicted exactly rather than just statistically. Einstein did not specify what type of theory he had in mind to replace quantum mechanics, but others have suggested that the solution be sought in some type of quote-unquote hidden variable theory. In hidden variable theories, physical properties other than those we can yet measure would determine those events about which quantum mechanics can only make probability predictions. The mathematician John von Neumann proved long ago that no hidden variable theory can agree exactly with the predictions of quantum mechanics. The predictions have not all been examined, however, so there exists some possibility a hidden variable theory could be formulated that agrees with all observations that have been made. None has yet been produced that physicists find satisfactory. Okay. A second problem with the interpretation of quantum mechanics, which troubles even those who accept the theory, involves the idea of measurement. Schrodinger's wave equation can be used to describe how any system changes from one time to another. If the wave is known everywhere in space at one time, it can be predicted everywhere at a later time. However, knowing the wave intensity also allows for probability predictions of the results of measurements. When a measurement is actually made, the observer suddenly obtains exact information about at least one property of the system, such as its energy. This change from probabilistic to exact information has come to be called the reduction of the wave function. It has been proved that even if the interaction between the measuring instrument and the system being observed is taken into account, this reduction cannot be properly described by the Schrödinger equation. Various scientists have taken different attitudes towards this result. Some have championed the view that the consciousness of an observer plays a fundamental role in a reduction of the wave function. Others have argued that because quantum mechanics cannot account for reduction, it is incomplete. Perhaps the most widely accepted view is that reduction of the wave function always involves the interaction of a microscopic object, such as an electron, with a macroscopic system, the measuring instrument. When this interaction takes place, there is an irreversible change in the measuring instrument, and it is this change that results in the reduction of the electron's wave function. There may be some truth to this view, but it only solves part of the problem, because irreversibility itself is not completely understood. All right. Let me take a sip of water here. I know he's simplifying everything, but it's still like a lot of... I wasn't expecting it from the time travel book. I was really kind of expecting this to be sort of a silly book, to be honest. And maybe it will turn out to be that. I was trying not to make snap judgments ahead of time on it, but I did kind of think of it would be a little bit of just a silly, fun read. Not that it's not a great read so far. All right. The Einstein-Podolsky-Rosen paradox and Bell's theorem. Another problem concerning the interpretation of quantum mechanics derives from work by Einstein with Boris Podolsky and Nathan Rosen. In an article published in 1935, they pointed out that the predictions of quantum mechanics, in particular the idea of indeterminacy, in some cases were in conflict with what they considered to be a plausible criterion for reality. The situation envisaged was one in which a physical system that is originally a whole split into two parts that eventually became widely separated. The reality condition they imposed was that measurements done on one part of the separated system should not affect the other part of the system. An example of their analysis is an atom containing an electron and proton, each with spin angular momentum of h divided by 4 pi, but with total spin 0, which breaks apart so that the electron goes in one direction and the proton in another. Because of the conservation of angular momentum, the total angular momentum of the electron and proton remains 0 even when they are widely separated. If a physicist determines that the electron's spin lies along some direction, he can immediately infer that the proton's spin points in the opposite direction. The reality condition would then imply that the proton's spin was already determined to have this value before the measurement was made on the electron. An argument given by John Bell in 1964 dealt with the fact that Einstein's conclusion contradicts quantum mechanics. His finding, known as Bell's theorem, derives from statistical measurements of spin values of many correlated electrons and protons. It states that any theory satisfying Einstein's reality condition, that reality is a localized phenomenon and particles have determined properties, necessarily implies a relation among the results of a series of measurements. A series of experiments to test Einstein's reality condition and Bell's theorem have been carried out. The results do not support Einstein's reality condition, but instead support quantum mechanics. Research that employs quantum mechanics remains at the center of contemporary physics. One aspect of this research involves the search for approximate methods that can be applied with the basic principles of quantum mechanics in studies of situations that are so complex that they cannot be dealt with exactly. Much of the research is condensed matter physics is of this nature. An important discovery in this area is that in some situations the discreteness of physical quantities that usually occurs on the subatomic level can also occur on the macroscopic level. The quantized Hall effect, a property of electrical resistance of certain substances under the influence of electric and magnetic forces, is a recently discovered example of this. Another important area of research involves the attempt to include gravity among the phenomena that can be described by quantum mechanics. We are nearing the end of this chapter. Yeah, it's 29 pages, and we're on 24. Although there are no observations yet that require the use of a quantum theory of gravity, physicists believe that phenomena may occur inside black holes and may have occurred everywhere in the earliest moments of the universe. It has not yet been possible to formulate a consistent quantum theory of gravity, either by beginning with Einstein's non-quantum general theory of relativity or applying the usual ideas of quantum field theory. Currently, some physicists are pursuing an approach based on a quantum theory of strings, objects extended in one spatial dimension, as opposed to conventional particles, which are extensionless points. String theories may succeed in uniting gravity with other forces of nature in a unified quantum mechanical description of nature. Meanwhile, there is no doubt that quantum mechanics is the most successful theory of physical phenomena yet invented by the human mind. Again, writing in 1999. Substring theories and grand unification theories. In theoretical physics, superstring theories are mathematical models that describe fundamental particles as extremely short, about 10 to the negative 35 m, I would guess that is that meters, one-dimensional strings rather than as zero-dimensional points. It is imagined that these strings are capable of twisting, looping, combining, and separating. They are also assumed to exist in more than 4 dimensions, with the additional dimensions rolled up in a tight space. Superstring theories are extremely speculative and remain unproved by certain successful predictions of the models, but certain successful predictions of the models offer hope that they might eventually lead to a single theory of forces and particles. The earliest string theories have been used unsuccessfully in attempts to understand the strong nuclear force. They have since been combined with theories of supersymmetry, hence the name superstring. In theoretical physics, grand unification theories, GUTs, are attempts to describe 3 of the fundamental forces of nature, the strong, weak, and electromagnetic forces, as aspects of a single interaction. Grand unification theories also describe the 2 primary constituents of matter, quarks and leptons, as manifestations of a single type of subatomic particle. According to current theory, forces between subatomic particles are transmitted via the emission and absorption of vector bosons particles with 1 unit of intrinsic angular momentum. Theorists use a mathematical structure known as a gauge field to describe these fundamental interactions. The weak, strong, and electromagnetic interactions differ mainly in their strengths, as measured by the rest energies of their bosons and by the probability of boson emissions. In order to increase strength, the individual bosons are gluons, the strong force, photons, the electromagnetic force, and W and Z particles, the weak force. In GUTs, the difference between fundamental forces are seen to be the result of the fact that particles are observed at relatively low energies. If particles could be observed at very high energies, the 3 types of interaction would be found to have equal strength. In addition, quarks and leptons would behave similarly under these conditions. The energy at which this unification is expected is about 10 to the 14th power GeV, giga-electron volts, a trillion times higher than the energies of present-day experiments. While it may never be possible to examine such high-energy processes in the laboratory, it is thought that in the very early universe, a small fraction of a second after the Big Bang, the average energy of all particles was high enough for these particles to behave in the manner described by GUTs. One startling prediction of GUTs is that new interactions may exist involving vector bosons whose rest energy is 10 to the 14th power GeV. These interactions would allow 3 quarks to convert into a lepton, including the decay of protons and neutrons into leptons. The result of such decays would be a proton lifetime of 10 to the 31 power years. And evidence for this would defeat the long-held notion of the eternal stability of the proton. Experiments designed to detect these rare proton decays are being carried out, but no conclusive evidence has been obtained. Although the validity of GUTs is not yet established, physicists are developing theories that will link the fourth force, gravitation, and its boson, the graviton, with the other 3 forces. These models are referred to as supersymmetry theories. Okay. Symmetry in theoretical physics. We got one paragraph here, and then I got a couple pictures to show you. In physics, a system is said to exhibit a symmetry if it remains unchanged under a given operation. For example, a ball looks the same under rotation in any direction about its center. The ball is therefore said to have a spherical symmetry. Such symmetries play a fundamental role in the understanding of various physical phenomena. They are an especially important part in the study of elementary particle physics, where the exact nature of the force laws is still unknown. The significance of symmetry is that many aspects of the behavior of the system may be predicted on the basis of its symmetry without a detailed knowledge of its inner workings. Okay, now we've got a few pictures here, and then we've got two more pages, and then a few more pictures, and we're done with this chapter. So this one, this is very small writing. An inventor of a time machine demonstrates it by sending the family cat back in time. An illustration from Ray Palmer's story, The Time Tragedy, for Wonder Stories, December 1934. Palmer went on to become the editor of Amazing Stories, a magazine which began the Shaver mystery and eventually led to Fate magazine, which told true stories of time travelers, UFOs, and other supernatural phenomena. So here is that illustration. I'll have to back off a little bit so you can see the whole thing. Okay, and I'll come in and pan up. Okay, all right, and then the next one, Thomson's Time Traveling Theory. A double-page illustration of the story Thomson's Time Traveling Theory by Malcolm Smith, published in Ray Palmer's Amazing Stories, 1944. In the story, a time machine inventor makes an experimental test of the so-called grandfather paradox by going back in time and killing his grandfather. That is this one. I'll have to get really close to it. There we go. Ooh, turn that a little bit. Okay, and then one last one, and then we'll get back to the reading. A light cone with space-like and time-like world lines after Naheen, 1993. Okay. So we've got the forward time-like, space-like, elsewhere, here, now, past, backward time-like, and future. So, yeah. All right. Moving on to the last 2 pages here. All symmetries may be classified into two types, discrete and continuous. For a discrete symmetry, there are only a finite number of operations that can lead to identical physical configurations. For example, a square drawn on a paper has a discrete symmetry because there are only 4 ways it can be rotated about an axis perpendicular to the plane of the paper to look unchanged. On the other hand, a circle drawn on a piece of paper looks unchanged after rotation through any angle about an axis perpendicular to the paper. Thus, the circle exhibits a continuous rotational symmetry. Some other examples of continuous symmetries are space-time translations and rotations. The former refers to all points in space and time being equivalent as far as physical laws are concerned. The latter refers to the equivalence of all directions in space, isotropy of space. Two important examples of discrete symmetry are space reflection and time reversal invariance. Many physical laws are unchanged under mirror reflection and under the reversal of the direction of time. A conservation law states that some physical parameters of a system remain unchanged during the time evaluation of the system. For example, in classical non-relativistic physics, the total mass of a system is fixed before and after, for example, a collision process, the conservation law for mass. Similarly, the total linear and angular momentum of the total energy of a system obey observation laws in both relativistic and non-relativistic physics. Since the advent of Lagrangian formulation of physics, it has been established that the existence of conservation laws is related to the existence of underlying symmetries. For example, the conservation of linear momentum is a direct consequence of invariance and of the Lagrangian under space translation, or homogeneity of space. Similarly, conservation of energy follows from invariance under time translation. The conservation of angular momentum is a result of rotational invariance. Symmetry under space reflection leads to parity invariance. In order to discover the nature of the conservation laws operating in a system, the nature of the forces in the system and the associated symmetries must be studied. Because all forces derive their origins from this potential energy, it is enough to study the potential energy to discover conservation laws. For example, the Earth and the Sun attract each other through a force that depends only on the distance between the two and not on their orientation, a central force. The force law is rotationally invariant and thus leads to conservation of angular momentum. Because the direction of angular momentum is perpendicular to the plane of rotation, the Earth and Sun are locked in the same plane forever. Thus, any two bodies interacting through a central force will have this property. Symmetries allow only certain final states once the initial state is given, implying in turn that appearance of many final states is forbidden, or at least highly improbable. The rules governing such transitions are called selection rules and are important in the study of atomic systems, where knowledge of allowed initial and final states determines, for example, the intensity and energy of the emitted light of lasers. Internal symmetries and space-time. The symmetries discussed so far involve space or time or both. Certain symmetries, though, are known to exist where the symmetry operation changes any type of particle into another. For example, it is known that in the nucleus, the same force exists between a proton-proton, proton-neutron, and neutron-neutron pair, meaning that there is a substitution symmetry between the proton and the neutron. In an imaginary space where the proton and the neutron form two hypothetical directions, any rotation in that space will leave the nuclear forces unchanged. This feature is called isopin symmetry. The inclusion of additional particles in such a space leads to the higher unitary symmetries. Other examples of internal symmetry are electric charge, baryon number, and so on, which also owe their origin to operations in a fictitious internal space. The internal symmetries may operate the same way or be different at each space-time point. In the latter case, they are called gauge symmetries. In the 1960s, theorists applied gauge symmetry to the concepts of both the weak and electromagnetic forces. They considered the idea of, quote, spontaneous symmetry breaking, end quote, in which certain relations in theory can have exact symmetry, yet in their physical manifestations do not provide neat representations of the symmetry. The result was a single mathematical model that incorporated both forces, the electroweak theory. What we have learned is that the fabric of space exists in different dimensions and time, as we know it. The fabric of space exists in different dimensions and time, as we know it, does not exist in the same way in all of these dimensions. It is theoretically possible to tunnel through time by accessing hyperspace. Incredibly, physics tells us that all things in the universe are interconnected through the various fields: gravity, electricity, magnetism, the weak force of atomic structure, and time. In theory, there is no barrier in time travel. Rather, time travel and time anomalies are part of the fabric of the universe itself. And that is the end of that chapter. And he's got a few pictures here. That I will go ahead and show this time. And then we'll call it. I'm not sure. I think we're done with the heavy physics stuff. Just kind of looking ahead. There's some, but it seems like it's not such a concentrated bunch of physics all at once. So, anyway, not good, bad, or indifferent. I'm just saying. Okay. Tilted light comes in a rotating universe after Nahim 1993. So here's the first illustration. It's just this top little portion here. Okay. The bottom half of that page says future light cones point almost entirely in plus t direction, far from rotating matter. They begin to tip over as the matter is approached. Note that there is a helical, time-like path that moves locally into the future in the negative t direction. In other words, it goes into the past as seen by an observer far from the rotating matter. The world lines of rotating matter are helixes in the plus t direction, after Nahim 1993. So there's that one. Need to get it closer there. Come on, focus. I can't read those words. Come on. It's a little bit out of focus, isn't it? Come on. There we go. Okay. Next, time tunnels and wormholes. These are unavoidably misleading two-dimensional interpretations of a time wormhole through three-dimensional space. The wormhole in A connects two disjoint universes, while those in B and C are connections in the same universe. The wormhole handle can either be long or short compared to the distance in external space between the wormhole mouths. There's that one. So A is two disconnected universes or connected universes, and the other two, B and C, are the same universe. Okay. Okay, now you're bringing in the I Ching. Cool. The 64 hexagrams of the I Ching, displayed in the traditional arrangement of a circle and a square. This ancient oracle allows a type of time travel, as it can predict coming events, or allow the user to change the future by acting as a two-dimensional representation of parallel worlds. Okay, so there's that. All 64 hexagrams. I don't know, is that clear? I don't know, I don't think we're going to get in close enough to get all that text. That's not too bad. That's an illustration you can easily look up online if you want to see it better. All right, we've got two more. Is it two more or three more? Three more. All right. A gigantic cyclonic waterspout observed in 1969 by NOAA aircraft near Key West, Florida. A good example of a vortex and how a three-dimensional media can suddenly become a one-dimensional filament spanning two separate dimensions of space-time. Okay. Is that an illustration bleeding through? No, it's not. I see a face there. Okay. Next page. From Tapping the Zero Point Energy by Moray B. King. And it's a table. A new viewpoint. Quantum effects arise from a matter zero point energy interaction. And there are two lists, quantum effect and quantitative explanation. I'll hold it up there and just let you all read it for yourselves. I'll just start at the bottom, get it into focus. Okay. All right, and then we've got one more page of illustrations, and I think these are just all okay. From Tapping the Zero Point Energy by Moray B. King. So it's two different squares. I'll just show them both to you at once. The zero point energy may arise from an orthogonal electric flux from the fourth dimension. Is what one is saying. So anyway, I'll show them to you. You can study them at your leisure. Okay, there's the first one. And then moving up to the second. And I'll back off just a little bit so you can see the whole thing. Okay, so that leads us to relativity and space-time curvature, from entropy to time reversal, invariance, and beyond. I don't think it's going to be quite as, maybe. Looks like there's going to be I see some more formulas and stuff there. So, and I'm not complaining, so don't take it that way. It just is not quite what I expected. I expected him to just be talking about kind of historical time travel stuff more. But that's okay. All right, so okay, after the second chapter, then we get into time bandits from the 1800s. So I think then he's going to start getting into the historical accounts, stories about time travel. So that will get a little bit easier to read. The Philadelphia Experiment, a history. So that'll be interesting. Pictures of Einstein. The Philadelphia Experiment, the technology. So that one might get a little bit more into physics again. But yeah, that's where we're going. That was a long enough chapter. I don't feel like I can do 2 chapters in one night. So we may just attack this one chapter at a time, which is fine. We know what our next book is, and it'll take us as long as it takes us to get to it. So, all right. Is this a book on quantum science? It is actually the Time Travel Handbook, edited by David Hatcher Childress. So, yeah. Figured why not? People voted on it, so we went for it. Universe A and Universe B, yeah. So, anyway, that'll be that for this session. I am going to attempt to play some Mass Effect 3 and not rage quit this time. Because I did last time. I was dying over and over and over, and I got pissed off and frustrated and quit. So we'll get back into it and see if I can make it through that battle without throwing too much of a hissy fit. So I'll end this session, and I'll be back in just a little bit to do exactly that. See you then.
Is broken on his feet because I have seen the apart. I have known possibility. I didn't have anything to say. Follow your heart, don't take. If you leave it behind, someone will bring. I left you my heart. What did you do? You left me all was my love? Was it dark? You have no answers. Don't know without you. How will I survive? You have no answers.